Hi, hello there. Welcome to designing IP addressing and selecting routing protocols. This video lecture begins with a discussion of the design of an IP address or IPv4 addressing scheme. It continues with an introduction to IPv6 or IP version 6 and a discussion of IPv4 to IPv6 migration strategies. Afterwards, it describes considerations for selecting the most appropriate network routing protocol. First, routing protocol features are discussed, followed by a description of various routing protocols appropriate for the enterprise use. The video discusses why certain protocols are suitable for specific modules in the enterprise architecture. It concludes with a description of some advanced routing protocol deployment features, including redistribution, filtering, and summarization. Let's get started. Designing IP addressing. Designing an IP addressing plan. This section explores private and public address types, how to determine the size of the network in relation to addressing plan, and how to plan an IP addressing hierarchy. This section concludes with a discussion of various IP address assignment and name resolution methods. Prerequisite knowledge. This includes IPv4 address and mask structure, IPv4 classes and CIDR or the CIDR, static addressing, dynamic addressing with DHCP, DNS, private and public addresses, the network address translation, and the port address translation, static network address translation, dynamic network address translation, and overloading. So these are the prerequisite topics prior to designing IP addressing. Private and public IPv4 addresses. Recall from the previous video that IPv4 or IP address space is divided into public and private spaces. That is for IPv4 and IPv6. Private addresses are reserved IP addresses that are used to implement within the company's network. So that is used internally within the organization's network, not on the internet. Private addresses must therefore be mapped to company's external registered addresses when sending anything on the internet. Public IP addresses are provided for external communication. The figure illustrates the use of private and public addresses in the network. So what are the guidelines for the use of private and public addresses in the enterprise network? Now, as shown here in the figure, the typical enterprise network uses both private and public IP addresses. So private IP addresses are used throughout the enterprise campus. Also, on the enterprise branch and enterprise teleworker modules. The following modules include public addresses. You've got the internet connectivity, where public IP addresses are used for internet connections and publicly accessible servers. You also have that on e-commerce module, where public IP addresses are used for the database, application, and web servers. The remote access and virtual private network or VPN module, the enterprise data center module, and the WAN and the metropolitan area network or MAN, and the site-to-site VPN module, where public IP addresses are used for certain connections. Network size and IP addressing planning. So determining the size of the network. So the first step in designing an IP addressing plan is determining the size of the network to establish how many IP subnets and how many IP addresses are needed on each subnet. So to gather this information, we need to answer the following questions here. First, how many locations does the network consists of? The designer must determine the number and type of locations. Next would be, how many devices in each location needs addresses? The network designer must determine the number of devices that need to be addressed, including end systems, router interfaces, switches, firewall interfaces, and any other devices. Next would be, what are the IP addressing requirements for individual locations? So the designer must collect information about which system will use dynamic addressing, which will use static addresses, and which systems can use private instead of public addresses. Next would be, what subnet size is appropriate? Based on the collected information about the number of networks and planned switch deployment, the designer estimates the appropriate subnet size. For example, deploying a 48-port switches would mean that subnets with 64 host addresses would be appropriate, assuming one device per port. Determining the network topology. Initially, the designer should acquire a general picture of the network topology. This will help determine the correct information to gather about network size and its relation to the IP addressing plan. With this general network topology information, the designer determines the number of locations, location types, and their correlations. For example, the network location information for the topology shown in the figure is shown in the table on the next slide. Okay, so basically, this includes the size of individual locations. So the network size in terms of the IP addressing plan relates to the number of devices and interfaces that needs an IP addresses. To establish the overall network size in a simplistic way, the designer determines the appropriate number of workstations, servers, the IP phones, router interfaces, switch management, and layer 3 interfaces. This also includes firewall interfaces, okay, or the other network devices at each location. Okay, now this estimate provides the minimum overall number of IP addresses that are needed for the network. So the table provides an IP addresses requirements by location for the topology shown in the figure from the previous slides. So some additional addresses should be reserved to allow for seamless potential network growth. The commonly suggested reserve is 20% for the main and regional offices and 10% for remote offices. However, this can vary from case to case. The designers should carefully discuss future network growth with the organization's representative to obtain a more precise estimate of the required resources. Planning the IP addressing hierarchy. So the IP addressing hierarchy influences network routing. This section describes IP addressing hierarchy and how it reduces routing overhead. This section discusses the issues that influence the IP addressing plan and the routing protocol choice, including summarization, fixed length subnet masking or the FLSM, variable length subnet masking or the VLSM, and a classful and classless routing protocols. So benefits of hierarchical addressing. So a network designer decides how to implement the IP addressing hierarchy based on the network's size, geography, and topology. In a large network, hierarchy within the IP addressing plan is mandatory for a stable network, including stable routing tables. For the following reason, a planned hierarchical IP addressing structure with room for growth is recommended for networks of all sizes. So this includes influence of IP addressing on routing. Okay, so an IP addressing plan influences the network's overall routing. Before allocating blocks of IP addresses to various parts of the network and assigning IP addresses to devices, consider the criteria for an appropriate and effective IP addressing scheme. So routing stability, service availability, network scalability, and modularity are some of the crucial and preferred network characteristics that are directly affected by IP address allocation and deployment. So the next one would be the modular design and scalable solutions. So whether building a new network or adding a new service on top of the existing infrastructure, a modular design helps to deliver a long-term scalable solution. So IP addressing modularity allows the aggregation of routing information on hierarchical basis. Next would be route aggregation. So route aggregation is used to reduce the routing overhead and improve routing stability and scalability. So, however, to implement route aggregation, a designer must be able to divide the network into contiguous IP address areas and must have a solid understanding of IP address assignment, route aggregation, and hierarchical routing. So also, there is a summarization groups. So to reduce the routing overhead in a large network, a multi-level hierarchy might be required. The depth of the hierarchy depends on the network size and the size of the highest level summarization group. So the figure here shows an example of network hierarchy. So a typical organization has up to 3 levels of the hierarchy. So the first level, the network locations typically represented the first level of the hierarchy in the enterprise network. So each location is typically represents a group of summarized subnets known as summarization group. So the second level, so a second level of hierarchy can be done within the first level summarization group. For example, a large location can be divided into smaller summarization groups that represents the buildings or cities within that location. Not all first level summarization groups require a second level of the hierarchy. Okay? And you've got also the third level. So to further minimize the potential routing overhead and instability, a third level of the hierarchy can exist within the second level summarization group. Okay, so for example, sections or floors within the individual buildings can represent the third summarization group. So route summarization groups. So what are the impact of poorly designed IP addressing? So a poorly designed IP addressing scheme usually results in IP addresses that are randomly assigned on as needed basis. In this case, the IP addresses are most likely dispersed through the network with no thought as to whether they can be grouped or summarized. A poor design provides no opportunity for dividing the network into contiguous areas. Okay? And therefore, no means of implementing route summarization. Now, the benefits of route aggregations. Implementing a route aggregation on a border routers between contiguously addressed areas controls the routing table size. Okay? So let's have an example of the hierarchical IP addressing and summarization plan. Okay? Now recall that the number of available host addresses on a subnet is calculated by the formula 2 raised to h, okay, or any variable minus 2. Okay, so where h is the number of host bits. Okay, so the number of bits set to 0 in the subnet mask. So the first 2 columns in the table shows the location and the number of IP addresses required at each location for the sample network. So the third column in this table is the next higher or the next highest power of 2 from the required number of addresses. this value is used to calculate the required number of host bits. Okay? And then assuming that the class B address, for instance, 172.16.0.0/16 is used to address this network. So you might have the fifth column, okay, illustrate sample address blocks allocated to each location. Okay? So basically, if the San Francisco campus requires 1,290, so you won't be getting an exact 1,290. So based on our formula, 2 raised to h, that would yield to 2,048. So if you need 441, that would yield to 512. Okay? And then if you need 21, so you could get 64 there. Of course, with the consideration of the future growth. All right. So this is a complete address block by location for San Francisco campus. So using the 172.16.0.0 address block, that is a Class B network. And after the careful planning for the redistribution of IP addresses, so we have come up with this assignment of IP addresses per location. Okay? So there are online tools that you can use to come up with this type of table. Okay, so you don't have to manually compute, okay, the number of hosts needed, and of course the division of the addresses within the block. You just have to use that application. You can go ahead and search that on the internet. Okay, so another example is the hierarchical IP addressing plan. Okay, so take note that from the topology that we have, so basically that comprises of the San Francisco campus, the Denver region, and the Houston region. So summarization point basically is on the edge network. Okay, so if it is on the Denver region, so that happens on the router connected to San Francisco campus. So details of routing remain within the area, simplifying routing tables and reducing processing time. So if you want to know more about this IP addressing scheme, you can go ahead and check the videos or the provided videos, okay, or the supplementary videos. All right, so next would be, so on the summarization point, okay, only summarized route, for instance, 172.16.8.0/22 is propagated on the rest of the network. So basically, it will not propagate addresses within the block. So it has to be summarized at some point on the network to simplify and to minimize the use of the resources. So for the main campus, 2,048 addresses are allocated. So 11 host bits are required. Okay. Now this subnet is further divided into smaller subnets supporting floors or wiring closets. Now for the Denver region, 1,024 addresses are allocated. 10 host bits are required. Okay. Now this address block is further divided into smaller subnets supporting buildings, floors, or wiring closets. So that's how you plan distribution of IP addresses within the network. And similarly, for the Houston region, so there are about 1,024 addresses which are also allocated and further subdivided, okay, as shown in the table from the previous slide. All right, so on this table here, you've got Houston. Now this figure illustrates one of the links in the Denver region going down and how summarization is performed to reduce the routing update, okay, or the traffic generated by those routing updates. Managing IP addresses. So there are a lot of ways on how to manage IP addresses. So some includes using DHCP in the enterprise, using DNS in the enterprise, and of course, using the network address translation on the enterprise. Now, using DHCP to assign an IP addresses. So DHCP or Dynamic Host Configuration Protocol is used to provide dynamic IP address allocation to hosts. So DHCP uses a client-server model. The DHCP server can be Windows server, a Unix-based server, or it could be a Cisco iOS device. So Cisco iOS devices can also be DHCP relay agents and DHCP clients. Now, using the DNS or the domain name system for name resolution, so to resolve symbolic names to actual network addresses, applications use resolver or the name resolver programs, which are usually part of the host operating system. An application sends a query to a name resolver that resolves the request with either the local database, host file, or the DNS server. Now, when numerous hosts or names must be resolved to IP addresses, statically defined resolution in hosts are widely to maintain. Okay? So to ease this process, DNS is used for name resolution. So DNS is a client-server mechanism used to access a distributed database providing address-to-name resolution. So a DNS server is a special software that usually resides on a dedicated hardware. So DNS servers are organized in hierarchical structure. A DNS server can query other DNS servers to retrieve partial resolutions for a certain name. For example, one DNS server could resolve, say, cisco.com, and another could resolve www. Okay? So next would be the use of the network address translation or NAT. This is a process in which one or more local IP addresses is translated into one or more global IP addresses and vice versa in order to provide internet access to the local hosts. Now, recommended practices for IP address assignment. So we have the method here is either you assigned it, okay, statically, or you assign it dynamically. So strategic address assignment, so infrastructure devices such as routers and switches should be given static IP assignment. Okay. Now for the DHCP, of course, the end user devices, just like for instance, if you are providing a free Wi-Fi access to the end users, so we could put it in a DHCP or dynamic assignment. Okay. Now, number of end user devices. So, well, for static, it could be up to 30 end user devices. So, if it is more than 30, then it is recommended to use DHCP. So, it's very hard to manually assign an IP address on multiple devices. Now, renumbering criteria, so requires manual reconfiguration for all the hosts. Okay, whereas for DHCP, only the DHCP server reconfiguration is needed. So address tracking, so it's easy address tracking for the static, whereas for dynamic, it requires additional DHCP server configuration. Now, additional parameters, manual configurations of all hosts are required. Now, for DHCP, only the DHCP server needs to be configured. Now, for high availability, IP addresses are available at any time. For DHCP, so redundant DHCP server is required. Now, for security concerns, well, we've got minor security risk for this static assignment. Okay? And then for dynamic, so any device gets an IP address. All right. Okay. So let's have an IP assignment or IP address assignment methods in an enterprise network. So what are the guidelines for assigning IP addresses in the enterprise network? So the typical enterprise network uses both static and dynamic addresses assignment methods. So as shown here in the figure, the static IP address assignment method is typically used for campus network infrastructure. Okay? And in all the modules of the enterprise edge, the e-commerce, the internet connectivity, the remote access and VPN, and the WAN and MAN and site-to-site VPN modules. Now, static addresses are required for systems such as server or network devices, in which the IP address must be known at all times for connectivity. So, general access or management. All right. So, whenever you assign an IP address to the server or router interfaces or switches, okay, so for management purposes, it is better to do a static assignment on them. Okay. So also on the server farm, so it should be given a static IP assignment. Now for the end user, we have to use dynamic. So dynamic IP addresses or address assignment is used for assigning IP address to end user devices. So including workstations, IP phones if you have IP phones, and mobile devices on the network. Static versus dynamic name resolution. So names are used to identify different hosts and resources on the network and to provide user-friendly interaction with computers. A name is much easier to remember than an IP address. Okay? Now, this section covers the purpose of the name resolution, provides information about different available name resolution strategies, and discusses the domain name systems or DNS name resolution. Now, let's focus on the static versus dynamic. Okay? The process of resolving a host name to an IP address can either be static or dynamic. Now, following are the differences between these two methods. Okay? Now, let's start with static. Okay? Now, for the static, with static name to IP address resolution, both the administrative overhead and the configuration are very similar to those of the static address assignment strategy. So the network administrator manually defines name to IP address resolutions by entering the name and IP address pairs into the local database or the host file using either a graphical or text interface. Okay? And then manual entries create additional work for the administrator. So they must be entered on every host and are prone to errors and omissions. That's a problem with static. All right. Now for dynamic, the dynamic name to IP address resolution is similar to dynamic address assignment strategy. The administrator has to enter the name to IP address resolutions only on a local DNS server rather than on every host. So the DNS server then performs the name to IP address resolution. So renumbering and renaming are easier with dynamic name to address or IP address resolution method. Recommended practices for name resolution. Okay, so to select the desired name resolution method, the following questions should be answered. Okay, so first would be how many hosts required name resolution. Okay, the number of hosts. Again, for static, up to 30 hosts, and then if it is more than 30 hosts, then go for dynamic name resolution. All right, next would be are applications that depend on the name resolution present. So that should be answered. All right, application depending on the name resolution. So if in static name resolution, it is not recommended. Now it is more or best recommended on dynamic name resolution. Okay, so next would be is the network isolated or it is connected to the internet. So isolated network, well, static is applicable, and so with dynamic. Okay, next would be if the network is isolated, okay, how frequently are new hosts added and how frequently do names change? Okay, so these are the recommended practices for name resolution, both for the use of the static name resolution and dynamic name resolution. Using DNS for name resolution. The figure illustrates the process of resolving an IP address using DNS server. Okay, so in here, step 1, okay, a user wants to browse maybe myweb.com. Because the host does not know the site's IP address, it queries the DNS server. Okay, now step 2, okay, so step 2 would be the DNS server responds with the appropriate IP address, for instance, for www.mywebs.com. All right, and then step 3, the host establishes a connection to the appropriate IP address, which is www.myweb.com site. Example of locating DHCP and DNS servers in the network. So DHCP and DNS server locations in the network, as illustrated in this diagram here, okay, the DHCP and DNS servers can be located at multiple places in the network, depending on the service that they support. Okay, now for the enterprise campus, DHCP and internal DNS servers should be located on the server farm. These servers should be redundant. Now for the remote location, okay, routers can provide DHCP and DNS at the enterprise edge. Okay, now external DNS servers should be redundant. For example, at 2 service provider facilities, or 1 at a service provider facility and 1 in a demilitarized zone or DMZ at the enterprise campus or remote data center. IPv6 address structure. So let us introduce IPv6. So IPv6 is a technology developed to overcome the limitations of the current standard IPv4, which allows end systems to communicate and forms the foundation of the internet as we know it today. Now, this section on IPv6 specific design considerations provides an overview of IPv6 features and addressing and explains the various IPv6 address types. Now, the address assignment and name resolution strategies for IPv6 are explored. So the transition from IPv4 to IPv6 is discussed, and the section concludes with brief description of the IPv6 routing protocols. Now, let's talk about the IPv6 address format or the structure. So rather than using dotted decimal format, so IPv6 addresses are written as hexadecimal numbers with colons between each set of 4 hexadecimal digits, which is 16 bits, which we refer to as hextets. Okay, so we like to call this one as the colon hex format. So the format is this one here, okay, where X is a 16-bit hexadecimal field. So the sample address is provided. For instance, you've got this IP address or IPv6 address given to you here. Okay, now the key point here is, fortunately, you can shorten the written form of IPv6 addresses. Leading zeros within each set of 4 hexadecimal digits can be omitted, and a pair of colons can be used. Okay, so like what we have here, you've got a pair of colons. All right, so once within an address, that is to represent any successive zeros. So for example, the previous address can be shortened to the following. So initially you are given this long IPv6 addresses, okay, or IPv6 address. Now the shorthand notation applying that principle, okay, omitting consecutive zeros and replacing it with a pair of colons, so you'll have this simplified IPv6 address. Okay, again, the key point, a pair of colons can be used only once within the IPv6 addresses. So this is because an IPv6 address parser identifies the number of missing zeros by separating the two parts and entering 0 until the 128 bits are complete. Okay? Now, if two semicolons or if two colons notations were to be placed in the address, there would be no way to identify the size of each block of zeros. Okay? Now, similar to IPv4 subnet mask can be written as a prefix. For example, /24. IPv6 uses prefixes to indicate the number of bits of network or subnet information. Now, let's talk about IPv6 features. Okay? The ability to scale networks for future demands requires a limitless supply of IP addresses and improved mobility. IPv6 combines expanded addressing with a more efficient and feature-rich header to meet these demands. Now, IPv6 satisfies the increasingly complex requirements for hierarchical addressing that IPv4 does not support. So what are the main benefits of IPv6? Okay, so first, you've got largest or larger address space. So IPv6 addresses are 128 bits compared to IPv4's 32 bits. This larger addressing space allows more support for addressing hierarchy levels, as much greater number of addressable nodes, and simpler auto-configuration for addresses. Okay? Next would be globally unique IP addresses. So every node can have a unique global IPv6 address, which eliminates the need for the network address translation. Okay? How about site multi-homing? So IPv6 allows hosts to have multiple IPv6 addresses and allows networks to have multiple IPv6 prefixes. Consequently, sites can have connections to multiple ISPs without breaking the global routing table. All right. So next would be header format efficiency. So a simplified header with a fixed header size makes processing more efficient. Next would be improved privacy and security. So IPsec is the IETF standard for IP network security. So available for both IPv4 and IPv6. Although the functions are essentially identical in both environments, IPsec is mandatory in IPv6. So IPv6 also has optional security headers. Next would be flow labeling capability. A new capability enables the labeling of packets belonging to a particular traffic flows for which the sender requests special handling, such as non-default quality of service or QoS or real-time service. The last one would be increased mobility and multicast capabilities. So mobile IPv6 allows an IPv6 node to change its location on an IPv6 network and still maintain its existing connections. So with mobile IPv6, the mobile node is always reachable through one permanent address. So a connection is established with a specific permanent address assigned to the mobile node, and the node remains connected no matter how many times it changes locations and addresses. IPv6 address scope types. So let's talk about the IPv6 address types here. This section covers various IPv6 address types and their scopes. Okay, so IPv6 address scope types. So similar to IPv4, a single source can address datagrams to either one or many destinations at the same time in IPv6. Okay, so following are the types of IPv6 addresses. So you have the unicast or one-to-one, similar to an IPv4 unicast address. An IPv6 unicast address is for single source to send data to single destination. A packet sent to a unicast IPv6 address goes to the interface identified by that addresses. So the IPv6 unicast address space encompasses the entire IPv6 address range with the exception of the FF00:8 range. Okay, so addresses starting with binary 11, 11, 11, 11 are all ones of 8 bits, which is used for multicast addresses. Now, the IPv6 unicast addresses, okay, is discussed on different types of IPv6 unicast addresses from different sections. Okay. Now, this is just to give you an overview about these scope types here. Next would be Anycast or one-to-nearest. So an IPv6 Anycast address is a new type of address that is assigned to set of interfaces on different devices. An Anycast address identifies multiple interfaces. So a packet that is sent to an Anycast address goes to the closest interface as determined by the routing protocol being used, identified by the Anycast address. So therefore, all nodes with the same Anycast address should provide uniform service. Anycast addresses are syntactically indistinguishable from global unicast addresses because Anycast addresses are allocated from the global unicast address space. Okay? So next would be the multicast or one-to-many. So similar to IPv4 multicast, an IPv6 multicast address identifies a set of interfaces in a given scope, typically on different devices. A packet sent to multicast address is delivered to all interfaces identified by the multicast address in a given scope. So IPv6 multicast addresses have a 4-bit scope identifier or ID to specify how far the multicast packet may travel. Okay? So IPv6 has no concept of broadcast addresses. Multicast addresses are used instead. IPv6 address types focus on the link local and site local addresses. Okay? Now for the link local address, so the key point here is every IPv6 enabled interface must contain at least one loopback. Okay, so that is ::1/128 and one link local address. So optionally, an interface may have multiple unique local and global addresses. So a link local address is useful only in the context of the local link network. Each scope limits its relevance to only one link. Okay? Now, a link local address is an IPv6 unicast address that can automatically configured on any interface by using the link local prefix FE80::10 and the 64-bit interface identifier shown on the figure. Okay? Now, link local addresses are used in the neighbor discovery protocol and the dynamic address assignment process. Now, what is a site local address? So, a site local unicast address are another type of IPv6 unicast addresses. However, the use of the site local or the site local addresses was deprecated in September 2004. Okay, so site local unicast addresses were similar to private addresses in IPv4 and were used to address a site without having a global prefix. Okay, now the site local addresses used the prefix FEZ0, okay, ::10 and an interface identifier concatenated after the prefix. So the site local addresses were considered private addresses to be used to restrict communication to a limited domain. So IPv6 routers must not advertise routes or forward packets that have site local source or destination addresses outside the site. How about the IPv6 address types global aggregatable? So let's start with a key point. IPv6 global aggregatable unicast addresses are equivalent to IPv4 unicast addresses. So the structure of a global aggregatable unicast addresses enables summarization or aggregation of routing prefixes so that the number of routing table entries in the global routing table can be reduced. So global unicast addresses used on links are aggregated upward through organizations and then to immediate or intermediate level ISPs and eventually to top level ISPs. IPv6 address assignment strategies. So basically, if you're planning to migrate or use IPv6, so for the static assignment, it's same with IPv4. Okay. Now for dynamic, so you have to consider either the use of the link local, the stateless, and stateful using DHCP version 6. How about the IPv6 name resolution? So this section discusses IPv6 name resolution strategies and name resolution on a dual stack, IPv4 and IPv6 host. So when you have heard of the term dual stack, that pertains to IPv4 and IPv6 running on the network. Now for the IPv6 name resolution, it's either static or dynamic. Okay. Now static name resolution accomplished by manual entries in the host's local configuration files. Now dynamic name resolution accomplished using a DNS server that supports IPv6, usually along with IPv4 support. Now as shown here in the diagram, an IPv6 aware application requests the destination host name's IPv6 address from the DNS server using a request for an A6 record. Now, an A6 record is a new DNS feature that contains an address record for an IPv6 host. So the task of querying for the address is done with the name resolver, which is usually part of the operating system. So the network administrator must set up the appropriate DNS server with IPv6 support and connect it. How about IPv4 and IPv6 aware applications and name resolution? So a dual stack host has both IPv4 and IPv6 protocol stacks and has a new application program interface or API defined to support both IPv4 and IPv6 addresses and DNS requests. So an application can use both IPv4 and IPv6. An application can be converted to the new API while still using only IPv4. Now, as shown in the figure here, an IPv6 and IPv4 enabled application chooses which stack to use. So the typical default is IPv6, okay, and asks the DNS server for the destination host's address. In this example, it requests the host's IPv6 address. Okay. Now, after receiving the response from the DNS server, the application asks the source host to connect to the destination host using IPv6. IPv4 to IPv6 transition strategies and deployments. Okay, so IPv4 and IPv6 migration does not happen automatically. The following section explores the differences between IPv4 and IPv6 and then discuss possible transition, okay, or different strategies and deployments. So the first one would be IPv4 and IPv6 transition. Okay, from IPv4 to IPv6 will take several years because of the high cost of upgrading equipment. So in the meantime, IPv4 and IPv6 must coexist. All right. So the following are the three primary mechanisms for the transition from IPv4 to IPv6. Not all organization has migrated to IPv6. There are some organizations who are still running their network on IPv4. Okay? So the first mechanism is a dual stack. Both the IPv4 and the IPv6 stacks run on a system that can communicate with both IPv6 and IPv4 devices. Okay? So the next one is tunneling. Okay? Tunneling uses encapsulation of IPv6 packets to traverse IPv4 networks and vice versa. Next would be translation. This is a mechanism that translates one protocol to the other to facilitate communication between the two networks. So let's deal with each of this mechanism. Let's start with the dual stack mechanism. Now, as shown here in the figure, a dual stack node enables both IPv4 and IPv6 stacks. The IP version choice is based on the name lookup and application preference. So this is the most appropriate method for campus and access networks during the transition period. And it is preferred technique for transitioning to IPv6. So a dual stack approach supports the maximum number of applications. Tunneling mechanism, okay, or the tunneling transition mechanism. The purpose of tunneling is to encapsulate packets of one type in packets of another type. So when transitioning to IPv6, tunneling encapsulates IPv6 packets in IPv4 packets as shown on this figure. Okay? By using an overlay tunnels, isolated IPv6 networks can communicate without having to upgrade the IPv4 infrastructure between them. Both routers and hosts can use tunneling. So it's either manually configured, semi-automated, and automatic. How about the translation transition mechanism? So a dual stack and tunneling techniques manage the interconnection of IPv6 domains. For legacy equipment that will not be upgraded to IPv6, and for some deployment scenarios, techniques are available for connecting IPv4 only nodes to IPv6 only nodes using translation, an extension of the NAT techniques. Now, as shown on this diagram here, an IPv6 network or node behind the translation device has full connectivity to other IPv6 nodes and uses NAT functionality to communicate with IPv4 devices here. Now, translation techniques are available for translating IPv4 addresses to IPv6 addresses and vice versa. Similar to current NAT devices, translation is done at either the transport layer or the network layer. So NAT protocol translation or the NAT PT is the main translation technique. The dual stack transition mechanism or the DSTM might also be available. IPv6 routing protocols. Since there are protocols or routing protocols for IPv4, there are also routing protocols for IPv6. So the routing protocols available in IPv6 includes interior gateway protocols or IGP for use within the autonomous system and exterior gateway protocols or EGP for use between autonomous systems. So IGP or the interior gateway protocol is used within the autonomous system. Autonomous system pertains to an area being maintained by a single administrator. Okay? And between different autonomous systems is basically that is where we use the exterior gateway protocols, or EGP, specifically BGP, or the border gateway protocol. Okay. Now, as with IPv4 CIDR, IPv6 uses the same longest prefix match routing. So updates to existing IPv4 routing protocols were necessary for handling longer IPv6 addresses and different header structures. So currently, the following updated routing protocols or draft proposals are available. So that includes RIP-NG, okay? For IPv4, RIP version 1 and RIP version 2. So for IPv6, it's RIP-NG, okay? Or the new generation RIP. For IPv4, EIGRP, okay? For IPv6, we also have EIGRP for IPv6. Now, OSPF version 2 for IPv4 and OSPF version 3 for IPv6. You also have the integrated ISIS. Okay, so this ISIS here were already obsolete, but it makes a huge comeback, okay, on the network that is currently being used on the implementation of the virtualization. Okay, now for the exterior gateway routing protocol, so a specific example is the border gateway protocol, or BGP. Okay, so let's summarize what we've talked about on designing IP addressing. So key components of an IPv4 addressing scheme includes IP address structure, address classes, subnetting, and masking. Well-designed hierarchical IP addressing enables efficient aggregation of routing advertisements, which consumes less bandwidth and router CPU. Okay? Now, dynamic address assignment is a recommended practice in the enterprise, specifically assigning an IP address to the end nodes. So, dynamic name resolution with DNS server is a recommended practice in the enterprise. So, IPv6 was designed as a successor to IPv4 to overcome IPv4 limitations. So, the IPv6 address structure and address types supports a much larger address space than IPv4. Okay, IPv4, you've got something like 4 billion. Okay, with IPv6, well, you have 100 or 340 undecillion. So could you just imagine the address space there? Okay, so IPv6 supports two address types: the link local and the global aggregatable.